Okay, physics fans, I've got a good one for you today, a little puzzle. Look at these symbols. What does it mean? Can you figure it out? Do you see it? Oh, wait a minute. I have it upside down. Sorry, let me turn it the other way around. Now do you see it? Oh, wait. Maybe you see it, maybe you don't. What is this all about? Well, let's keep going here. I'm going to help you out a little bit. So, how about if I flip the colors? Maybe that makes it easier. You were probably looking at the black symbols, but look at the space between those symbols. Those symbols are now white, and the space in between. Aha! It's becoming clearer. That original pattern actually contained the word energy. If you look closely, you could find it. You can rewind the video if you want to. Once you see it, it's one of these things that you can't not see it. Well, why do I have that in this video? What in the world am I thinking? Well, the study of energy is kind of seeing the world differently than we do before that in physics. So before we get to energy, we're doing things like F equals ma, force equals mass times acceleration. Cause and effect. Why does an object accelerate? Because there's a force. But now we're going to look at the same kinds of things, like here's an object rolling down a hill, but using a different way of looking at it. So that's why I like this puzzle as an introduction. It depends on how you look at it, what you see, and you're looking at it the same way, but a different way. Or you're looking at the same thing, but in a different way. So that's kind of what we do with energy. This unit is an interesting unit. It's a totally different way to do physics, a totally different way to look at it. So this is an alternative to Newton's laws. And a very different approach. If you've had trouble with Newton's laws, maybe conservation laws make more sense to you. It's a different way to do physics. It's kind of a different means to get to the same end in some ways. Here's a unit outline for this unit. The major topics will be energy, work. We'll look at springs and power. So these are the topics we'll run into in this unit. We're going to be using conservation of energy as a key idea. There are different kinds of energy, kinetic and potential. In this video, we're going to talk about two basic forms of energy and how to calculate kinetic and potential energy. And what is energy anyway? That's the other thing we'll talk about in this video. Our objective for this video is this one: define and apply the concepts of kinetic and potential energy. We're not going to do a whole lot with conservation yet in this video, but eventually that's kind of where you'll be heading. Here's a fun question. Do you have any energy today? Oh boy. You know what? I've been teaching all day long. It's the end of the day. I might be feeling a little run down, but I have some energy. What is energy anyway? If you have energy, what do you have? You might have heard a definition before. Maybe you've heard this one before. How do we define energy scientifically? The ability to do work. So, hey, well, I guess I have some energy. I'm still working today. I'm still doing some work. I'm still ticking. And that's our definition. Energy is the ability to do work. If you like physics, that might strike you as being a little almost vague in a way. The ability. We often have these really technical definitions in physics, like acceleration is the rate of change in velocity with respect to time. Very specific definition. This sounds a little wishy-washy for physics, but this is it. Now, one thing that we will need to clarify is what is work? What exactly do we mean by work? And at that point, we kind of have a chicken and the egg deal. Like, what came first, the chicken or the egg? What should I teach first? If I'm your teacher, what should I teach, energy or work? I like to start with energy because I think it's more interesting and I want to get your attention at the beginning of a unit. But we will say a little bit about work. So here are some things to know about work. This isn't really a strict definition, but in physics terms, work would be done when a force is acting over a certain distance. So I like to use a simple example. Let's suppose I go home today and I mow my yard. I have a push mower. It's not self-propelled. You can't ride on it. You have to push it. So if I go home and mow my yard, which, by the way, it kind of needs to be mowed. But if I go home and mow my yard, I'm doing work because I'm pushing my lawnmower, and I have to push it a certain distance. And that's definitely work. And I definitely need some energy, right? We all kind of intuitively should be able to make sense out of that. If you're pushing something, you need energy to do that, and you're doing work when you do that. Energy would be anything that would allow that to be done, whether it's done by a person or by something else. What else could push my lawnmower? Well, maybe an animal could push my lawnmower, but even something else. Let's suppose there's a car that's rolling through my yard for some mysterious reason, and it runs into my lawnmower. Could the car push my lawnmower? Yes, it could. The car might have the ability to push my lawnmower. Pretty much anything that could cause it to happen. Maybe a tree falls, and the tree, while it's falling, it happens to knock my lawnmower across the yard, and it's exerting a force that's moving my lawnmower. That would be doing work. So anytime there's a force causing something to happen, there's likely to be work at play. All right, so if I have energy, if I have the ability to do work, how are we going to measure that ability? Well, there is a unit called the joule. You might have heard of the joule in the different science class. The joule is a unit for measuring energy. It's also a unit for measuring work. So like I said earlier, work and energy, what comes first? It's like the chicken and the egg. Well, you can't have one without the other. So the joule is kind of interchangeable as a unit for energy or work. It is the amount of energy needed to do a certain amount of work. Exerting a force of 1 Newton over a distance of 1 meter would be an amount of work equal to a joule, requiring an amount of energy, 1 joule. You need energy to do work. It's in our definition. Energy is the ability to do work. So that means 1 joule is equivalent to 1 Newton times 1 meter. So if we think about my example with my lawnmower, if I exert a force of 1 Newton pushing my lawnmower 1 meter, I need 1 joule of energy to do that much work. If I actually have to exert a force of 100 newtons to push my lawnmower 1 meter, then I need 100 joules of energy to do that much work, and so on. So the joule is equivalent to newtons times meters. And that is also something you could break down to base units, kilogram meter squared per second squared. There are some other units for measuring energy that you might have heard of before. Here's a list. Calories. So if I'm going to mow my yard, I need some calories. Why are there 2 calories in this list? Well, you might recall calories from chemistry. That's the first one in the list. That's the lowercase calorie. That's a quantity that you might recall from chemistry. 1 calorie is the amount of heat needed to raise the temperature of 1 gram of water 1 Celsius degree. It's equivalent to about 4 joules. The other calorie really should be called a kilocalorie. It's 1,000 times greater. Capital C calorie, that's the one on a package of food. So if you eat something that has a calorie of energy in it, then that's 4,000 joules. So that might surprise you, but when you eat 100, say a little snack that's 100 calories, then that's 100 times 4,190 joules. That would make it 419,000 joules, right? And multiply by 100. Am I doing that right? I don't think I did that right. Add 2 zeros, and that's 419,000 joules. Yeah, if you had 100 calories. Anyway, a calorie of food energy is actually 4,000 joules roughly. BTU is called the British thermal unit. That's another unit for measuring energy. It's about 1,000 joules. So there are two types of energy that we're going to be looking at today, and I bet you have heard of them before. And I got some pictures here of the way that we run our society. So wind farm might be one source of energy, and then here I also have a hydroelectric dam. So what are these two types of energy? Well, a wind farm exploits kinetic energy, whereas a hydroelectric dam exploits potential energy. So have you heard of those before, kinetic and potential? How do we define these different types? What makes them different? Well, what makes them different is what they are due to. Due to what? Energy due to what is an interesting question. Kinetic energy is in the name. Kinetic refers to motion. Kinetic energy is energy due to motion. So it's energy that's coming from the fact that something is moving. If you think about a wind farm gets energy from air that's moving. So we can say that the air has kinetic energy. That kinetic energy allows work to be done. And the work done, well, part of what's happening is there's a force causing the turbine blade to rotate. And the air has the ability to rotate the turbine. So the air has kinetic energy when it is in motion due to the fact that it's in motion. So that's kinetic energy. If you make a similar statement about potential energy, it's not as obvious. A lot of times students are confused about potential energy. So energy is due to something. Potential energy is due to position and arrangement, and it's always associated with some sort of force. So if we think about, where is energy coming from with this hydroelectric dam? Well, it's by virtue of the fact that there's water behind the dam. That is an arrangement. It is a position. The water is positioned behind the dam. The water level on one side of the dam is higher than the water level on the other side of the dam. So again, it's the way it's arranged that matters. And associated with a particular force, well, you can guess what that force is. Why does the water go through the dam and turn the turbines? And what is causing that to happen? Gravity. If it weren't for gravity, it wouldn't matter that you had water behind the dam. We need gravity for the system to work. So this would be a type of potential energy associated with where the water is and the fact that there is gravity acting on the water coming from the earth. Gravity from the earth is pulling the water down. And when I have the water piled up behind this dam, then that represents the ability for work to be done. Gravity pulls the water through the dam. Ultimately, that causes turbines to turn, and then we can generate electric energy. There are all kinds of energy, by the way. So electric energy, nuclear energy, chemical energy, they're all types of energy. We're only going to focus on two today. And these are mechanical, sometimes referred to as mechanical energy. It's the energy associated with just ordinary matter by virtue of either the fact that it's moving or by the way it's arranged and some force that's acting on these objects or things with mass, mechanical energy. Okay, so let's move on. We want to learn how to calculate energy. So the last part of this little video will be introducing some formulas that are used to calculate two types of energy in joules, getting the amount in joules, and I have a couple of examples to show you. So let's take a look at them. Kinetic energy Mechanical kinetic energy is energy that an object or substance might possess because of the fact that it's moving. Technically, this is going to be translational motion. Later in the year, we'll study rotational motion. But translational motion is what we've been studying so far this year. To translate basically just means to move from one position to another. So when you do that, you have a certain speed, and you might have a certain mass. And if you have mass and you have speed, you have kinetic energy. Any object that has a certain mass and is moving at a certain speed has a certain amount of kinetic energy. Kinetic energy is equivalent to 1/2 mass multiplied by speed squared. Sometimes abbreviated KE for kinetic energy, pretty obviously, or in other cases you might see it abbreviated simply K. So sometimes you'll see it written like this, sometimes you'll see it written the other way, KE. I'm not going to be picky. I think AP programs typically will lean towards this notation, just K. But you'll see it both ways. Depends on what book you look at. It depends on who you ask. It depends on your preference, what your symbol would be for kinetic energy. But I would recommend one of those two. Those are the two most common. So what does that mean? Well, if an object has a certain mass and a certain speed, it has the ability to do work. Going back to my example of like pushing the lawnmower. Well, this might seem like a weird idea, but suppose, there was a hill nearby and a big round boulder rolled down the hill, and then the boulder was just headed towards my lawnmower for some reason. The boulder might have a certain mass and a certain speed, and by virtue of the fact that it's moving and it has inertia, that boulder, that rolling boulder, might push my lawnmower for me. Boy, that would be nice if I could get my yard mowed by rolling boulders. Okay, that's a wacky idea. But any object that's moving and has a certain speed could exert a force on another object by virtue of the fact that it's moving and it has inertia, tendency to keep going. So that's what we are calculating if we do this calculation, 1/2 mv squared. The greater the mass, the greater the speed, the more kinetic energy it's going to have. Let's look at a couple of examples of calculating kinetic energy. All right, so our first example, what if we had a bowling ball that was 5 kilograms moving with a speed of 10 meters per second? Those are plausible numbers. Typical bowling ball, typical speed for a bowling ball, perhaps at a bowling alley. We're going to ignore the fact that it might be rotating. Don't worry about that for now. But the type of energy that we're learning about is just associated with this. How much mass does the bowling ball have, and how fast is it moving? So let's crunch the numbers. 1/2 mv squared. Plug in 5. Plug in 10. Plug in the units. For this first example, at least, I want to show the units and talk about how that equates with energy. So 1/2 5 kilograms, and then the speed, 10 meters per second, quantity squared. So 10 squared is 100 times 5, that's 500 divided by 2, that's 250. And then think about the units. I'm going to square meters and seconds. And that's going to give me this combination of units. And that would be a combination equivalent to a certain number of Newton meters, and that is equivalent to a certain number of joules. So a bowling ball like this would have 250 joules of energy, kinetic energy. Hey, what's that? There goes another ball. That's a bowling ball going down. Actually, would that change my answer? If maybe it's not a bowling ball at a bowling alley, maybe it's just falling out of a tree. If it's falling out of a tree and moving at 10 meters per second, does that change the amount of energy? No, it does not. Doesn't matter what direction. Energy is a scalar. So bowling ball with that speed moving in any direction would have about 250 joules of energy. And remember, it's the ability to do work. What does a bowling ball usually do at a bowling alley? It moves pins. The skittles or pins they call them. You're trying to knock the pins down. Well, you have to push a pin a certain distance to knock it down. So this bowling ball could do that much work knocking down pins, for example. It might exert a force of 250 newtons pushing pins a distance of 1 meter when it collides with them. So that's what that means, and that's our first example of kinetic energy. Pretty simple, right? If we have the mass and speed, we just run these numbers, and then we know how many joules that is. Here's another example. Let's suppose we have a bigger object, a car, moving at some different speeds. So we'll just kind of play around with the numbers and see what happens to our amount. Hey, there went a car. Did you see it? If you have a certain car with a certain mass and a certain speed, your car has energy. 1,000 kilograms would be a really small car, like a subcompact car. But if you had that, at 10 meters per second, think about it, it would be like the bowling ball, but more mass. 1,000 kilograms is 200 times greater than 5 kilograms. So it's going to end up with 200 times as much 200 times as much energy when it's moving at the same speed because it has more mass. Energy depends on mass, but it also depends on speed. So if we crunch these numbers, and this time I left the units out, the units would always work the same. I would get 50,000 joules at 10 meters per second, 200,000 joules at 20 meters per second, and 450,000 joules at 30 meters per second. These are all speeds that a typical car might drive around. If you're in the neighborhood, you might be going 10 meters per second. On a highway, you might be going 20 meters per second. On the interstate, you might be going 30 meters per second, but these would be some plausible values. A joule by itself is not much energy, actually. So we often have values like this, kilojoules. Kilojoule means 1,000 joules. So that's kind of an interesting pattern. If your speed starts to climb, your kinetic energy climbs more. If you double or triple your speed, you more than double or triple your kinetic energy. Why should you care about that? Energy is the ability of your car to do work. If you're in an accident, bad things happen, and your car has more capacity to make bad things happen. And that's a fair physics statement. If your car has more kinetic energy and you're in a wreck, you can smash your car more. It takes work to smash a car. So that's something to keep in mind when you're deciding how fast to drive. As your speed increases, your kinetic energy goes up with the square of the speed. So if you double your speed, you have 4 times as much kinetic energy. If you triple your speed, you have 9 times as much kinetic energy. So it really starts to skyrocket on you as your speed climbs. The other type of energy that we're going to look at is potential energy of a particular type. So potential energy has several different varieties, I guess you might say. Previously, in the previous slide there, we said potential energy is associated with a force. So gravitational potential energy is the type involved with the hydroelectric dam. We have the water, but then we have gravity. We need gravity for it to work. Gravity is really what's going to cause that to be energy. Energy is the ability to do work. Work involves a force acting over a distance. This force is going to be gravity. Here's a formula for you. Potential energy, mgh. This one is really simple and kind of easier to understand and see the connection with the definitions. So potential energy, PE, equals mass times G, our good friend G, and H for height. So here are some definitions for you. Mass of the object, acceleration due to gravity or gravitational field strength, it's sometimes called, little g. Height above a reference, So we want to measure how high above something, above ground level, perhaps. And we can calculate potential energy with this little formula. Sometimes people like to use the symbol U for potential energy. And that's a common symbol. It's shorter, so that's nice. So this one would be fairly common. You'll see it in textbooks, and the AP program would typically use the symbol U for any type of potential energy. Why U? Let's not worry about that. We kind of run out of letters. P has some other uses in physics. So there's P for power, there's P for momentum, there's some different things that are abbreviated with a P. So for whatever reason, U is a common symbol for potential energy. Let's look at some examples. So here are some examples of potential energy. Let's go back to our bowling ball. Suppose we just set our bowling ball on top of a table. Might look something like this. Our bowling ball has a mass of 5 kilograms, sitting on top of a table that's, say, 0.6 meters high. What do we calculate if we get the amount of potential energy? Well, we're going to use that formula, mgh. Plug in the values. For the first example, I want to include the units just to kind of stress what's going on. And this one you should be able to make sense out of. So if energy is the ability to do work, work involves force acting over a distance, it's in the formula. When we multiply m times g, we get the weight or the force of gravity, 49 newtons. This bowling ball is pulled by gravity 49 newtons. If we multiply by 0.6 meters, that's a distance. Could 49 newtons act over a distance of 0.6 meters on this bowling ball? Yes, if the bowling ball comes off the table and moves to the floor, then that much work would be done by gravity. And that would be equivalent to a certain number of joules, about 29 joules, 29 newton meters. And this time it's pretty much literally exactly what the definitions say. Energy is the ability to do work. If the bowling ball moves to the floor, gravity will do that much work. That much force will act over that much distance, that much work, that many joules. So this would be the amount of energy when it's on the table. Hey, my bowling ball just moved. Did you see that? Doesn't matter if the bowling ball is moving on the table. Actually, it doesn't. As long as it's at that height, it could be on one end of the table, it could be on the other end of the table, and it could be moving. It doesn't have to be at rest to have this type of potential energy or to have this energy type. It could have some kinetic energy as well as potential energy at the same time. Oh, look, it's really close to the edge. Does it have more potential if it's at the edge? It might seem like the answer would be yes, like there's a greater likelihood that it falls off the table and makes something happen. But that's not correct scientifically. So we don't really care if it's about to fall off the table or if it's never going to fall off the table. It has this amount of energy based on our formula. Using the floor as a reference, this is how much energy it has as long as it's at that height. It doesn't matter if the table remains standing, the table could fall apart, the ball could fall off the table, but then its potential energy would change. As long as it's at that height above the floor, that's how much potential energy it has in this situation. One technicality is it's energy associated with the system, you might say. There's the ball and then there's the earth. If you don't have the earth, you're not going to have this energy. So if you have a table floating in space with no gravity, you don't have this energy. But we often would just say, okay, the ball has this energy. You need the earth too. If the ball were on the floor, its height would be 0. It can't fall any further than that or move any further down than that in this room, let's say. And then we might say, well, it has no potential energy when it's there. Like nothing's going to happen now. It has nowhere to go. So there's two examples actually with the ball initially on the table, 29 joules. If it were on the floor, then it would have 0 joules of energy. What if we take the same ball and put it on top of a cliff, a much higher location? So 60 meters would be 100 times greater height than the table. So what does that do to our energy? Well, just looking at the formula, I hope you can figure it out. It's the same mg, but it's a greater h, greater by 100. That's going to give us 100 times as much. Hey, look, I changed my picture. There's my ball on top of a cliff. Oh no, there's somebody at the bottom of the cliff. Oh, they're saying, yikes. What if I get smashed by this bowling ball that falls off of this cliff? Well, watch out, little dude. There's a fair amount of energy there. We can calculate it. Just crunch the numbers. It's 100 times higher. That's 100 times as much energy. So instead of 29 joules, now I've got 2,900 joules, or 2.9 kilojoules in this arrangement. Now, the height in the problem is interesting to think about. How do we know where to measure h from? There isn't one correct answer here. How you measure h is an arbitrary thing. It's a choice, actually, in a problem. Unless it's specified, say you're reading a problem, it might tell you to use a certain reference. But height is always just a vertical distance. It doesn't matter horizontally the location of your object. It's just how high above some reference level, you could say. In our first example, we were using the floor as our reference. In our second example, the base of the cliff was a reference for h. Wherever we're measuring from, that's our relative value, our number we calculate would be relative to that location. So the ball had 29 joules on a table. That means, really what it means is it has 29 joules more energy being on the table than it would have if it were on the floor. In our cliff example, the ball has 2.9 kilojoules more potential energy being on top of the cliff than it would have if it were at the bottom of the cliff. So that's what we mean when we say relative. When we're using this formula, we would always make m and g both positive, but h could be negative sometimes. So that might kind of hurt your head a little bit. We're going to look at an example before the end of this video. But h could be negative, but m and g would normally be positive quantities when doing this calculation. H would be negative if you're below whatever reference level you want to choose. A different way to think of this, though, and notice I changed my equation at the top of the screen. So sometimes you might see it written this way. Instead of u equals mgh, delta u equals mg delta y. And this is, for some people, a preferred way to think about it, so I'll just offer this. When we do that calculation, really what we're finding is the difference in energy one location versus the other. So delta y would be like a change in elevation. And if you have a change in elevation, you have a change in potential energy. If you go from the floor to the top of the table, your elevation changed by a positive 0.6 meters. And that means your potential energy increased by the amount that we calculated, 29 joules. If we go back to our ball on the cliff, hey, wait a minute, look at my picture. What is that? Oh no, the table was on top of that cliff the whole time. Who knew? Well, when we did the table problem, we were using the floor as a reference. But what if that floor is on top of a cliff? Couldn't that be true? Yes. If the ball's on the floor, which is on top of a cliff, you might say it has no potential energy. If you're using the floor, which is on top of the cliff, as your source of reference. But then if the ball moves to the bottom of the cliff, what do? Well, now it's below my chosen reference, 60 meters. And if we wanted to, we could say, well, now h is a negative value. So here's an example of a negative quantity for potential energy. Same number, but now negative, negative 2.9 kilojoules. We could say if the ball is at the base of the cliff, its potential energy is negative 2.9 kilojoules relative to the top of the cliff. So that might sound funny. How can you have negative the ability to do work? Energy is the ability to do work. Now we have negative the ability to do work. Sometimes you might feel like you have negative ability to do work if you're really tired. But in physics terms, really what it means is you have less energy in this location at the bottom of the cliff than you would have at the top of the cliff. This much less. And hopefully that makes sense to you. There's definitely more potential energy here if the ball is on top of the cliff. So this basically just means that much less than it would have being on top of the cliff. As I mentioned in the previous slide, some folks like to think of this as delta U. Delta U equals mg delta y. So look at my diagram. I added an xy coordinate system. If you go from the top of the cliff to the bottom of the cliff, the change in y is negative. You go from a positive y value down to 0. That would make your delta y negative. And then the same calculation gives you the same answer, but now we could describe it as saying, hey, we just calculated how much potential energy my ball lost if it went to the bottom of the cliff, having started on the top of the cliff. I hope these examples kind of help you see the arbitrary nature of potential energy. And whenever we calculate mgh, we need to interpret what it's telling us. It is always a difference in energy amounts depending on two locations. That's always definitely true. Just different ways to say it is really all that's going on there with the different notations and different wording. Okay. So I hope that you feel like you learned something with this video. What is energy? Ability to do work. Calculating kinetic energy, 1/2 mv squared. Calculating potential energy, mgh.